Okay. So, so, so what we are going to see is, given a binary search tree, what we need to convert it to a max heap or a min heap. So let us do a max heap first. So we do in two stages. First is, so given this binary search tree, we need to do what is called the in-order traversal for just the data of the nodes. So the in-order traversal rule is left, root, right. So we start with the root node, but don't list it, go to the left subtree. Don't list the root, go to the left subtree. So this is your root, but there's no left subtree, so we can list the root data, so which is 13. There's no right subtree, so done with this left subtree. So go to the root. Now that is data is 14, list it. Then go to the right subtree. There's no left child, so list the root data, which is 18. So done with this left subtree, go to the root. So the data is 22. Go to the right subtree. So this is the root. So go to the left subtree. There's no left subtree further down. So list this data 23 and go to the root, which is 27. So this is the in-order traversal of the data values in this binary search tree. Then to do a binary search tree to max heap conversion, you do what is called a post order listing of the node index values. So the post order listing, again the rule is left, right, root. So start with the left, sorry, root, go to the left, and then further go to the left. There's nothing further, we can go down. So we can, so there's no left or right, so list the root index, which is 3. Then list the right child index, which is 4. And then list the root with index, which is 1. Then done with the left subtree, go to the right subtree. Then for the right subtree, this is the root, and go to the left child, which is 5 index, so list it. And then there's no right child, so then go to the root index, which is 2. So done with the left subtree, right subtree, now list the root index, which is 0. So this is the post order listing of the node index entries. So all we have to now do is just superimpose the two. Okay, so at node index 3 we are going to have data 13, which is already there, that's okay. And then node index 4 we are going to have 14. So at index 4, instead of 18, we are going to overwrite that with 14. At index 1 we are going to have 18. So at index 1 we are going to have 18. At index 5 we are going to have 22. Index 2 we are going to have 23. And index 0 we are going to have 27. So this is a max heap. So you can cross check whether it satisfies the properties of a max heap. So for a max heap, it should the data should be like what? The data of any internal node should be greater than or equal to the data of its two child nodes. So this node, the data is greater than or equal to its two child nodes, then 18 greater than 13 and 14, 23 greater than 22. So this is a max heap. Of course, this we did not change the structure. So in order for this to be a max heap, it also has to be an essentially complete binary tree. So you're assuming that the given binary search tree is also essentially complete. So we need not worry about that. So we'll just check for the data property of the binary tree and make sure it's a max heap. Now we can do a similar thing for converting a binary search tree to a min heap. The only difference is for the node index we need to do a pre-order listing instead of post-order listing. So we still do the in-order traversal of the data of the nodes in the binary search tree and then do a pre-order listing of the node index entries and then superimpose the two. So again, the in-order traversal, the rule is left, root, right. So we can apply that and list the data of the nodes in this binary search tree. It will be 1, then 3, 4, then done with the left subtree. So the root is 5, then that is the root 5. Then for this right subtree, it's going to be this 5 followed by the root 6. Done with this left subtree, now list the root, which is 7, followed by the right subtree, so that is the root here, but go to the left subtree, so 8, then the root 9, then the right subtree 10. Then for pre-order, the rule is root left right, so start with the root, list it right away, so 0, so we're listing the node index 0, then go to the left subtree, list the root right away, which is 1, go to the left subtree, list the root right away, which is 3, then go to the left subtree, which is index 7. So now done with listing the root, so there's no thing further down. So what we have to do is go to the right subtree, which is index 8, and then done with this left subtree, listed the root already, go to the right subtree, so here list the root 4, then go to the left subtree, so which is index 9, then done with this, already listed the root, so go to the right subtree, list the root right away, which is 2, then go to the left subtree, which is 5, and then the right subtree, which is 6. So in pre-order, list always the root first of whatever the tree or the subtree, and then its left subtree, and then for the down, and then go to the right subtree for the down. So superimpose the pre-order and in-order listing. So for node index 0, we are going to have data 1. So at index 0, we are going to have data 1. At index 1, we are going to have data 3. And index 3, we are going to have data 4, and so on. So once you replace the data of the nodes based on the pre-order listing and the in-order listing of the data, we'll get a min heap, and you can cross-check whether for every internal node the data is less than or equal to the data of its two child nodes. So for here it is 1 less than 3 and 8, 3 less than 4 and 6, 8 less than 9 and 10, 4 less than 5 and 5, 6 less than 7. So this is satisfying the property for a min heap. Okay. Alright, so I have one more example which you can go through. It's a similar example. Okay. So with this we finish this module. So if you have any questions, you can type. You can also use your microphone and ask any question if you have. So let me just save this as a video.